This next section we're talking about is about fluids. For me, I don't know, maybe for you as well, when I think of fluid, I think about a liquid. And a liquid most certainly is a fluid, but a gas is as well. A fluid is anything that flows. So essentially, it needs a container to keep it in one space only. So both liquids and gases are technically fluids. Liquids are incompressible, meaning I can't force the same amount of liquid into a smaller container. Gases are compressible, which, like a bicycle pump, we can compress the gas into a smaller volume, and this in turn will change its density. So a couple of things that we need to talk about, a couple of definitions. With fluids, we talk about pressure when we're talking about the force they exert on something. So the force, for example, if I have a glass of water, the water itself exerts forces on the walls of the glass and the bottom of the glass. We don't typically talk about the force, we talk about the pressure that is exerted. So we're going to use a capital P, and actually your author might use a lowercase p, but P for pressure. Pressure is the ratio of force per area. So SI units, force is in newtons, area will be in meters squared. Another name for this is a Pascal. We will call this capital P sub A. Now, if you want to use newtons per meter squared and not write out pascals, that's totally fine. They're equivalent, but those are the SI units for pressure. So pressure, force per area. So for example, if my dog sits on my foot, silly example, I know, but if they actually sit, so their back end is on my foot, that's a terrible picture, I'm not artistically inclined, that feels different than if just their paw. If their paw and they stand on my foot versus they sit on my foot. The smaller area of their paw hurts. I feel that more, even though their weight overall is the same. And so it's this pressure, I'm feeling a larger pressure because the force is concentrated in a smaller area. So pressure is not just force, but how that force is distributed. Now, another concept we need to be familiar with is density. Density, this is called mass density. It's the mass per volume. Density is something that's unique to the material. So for example, water, H2O, has a density of 1,000 kilograms per cubic meter. So 1,000 kilograms per cubic meter. The symbol we use for density is the Greek letter rho, which you want to be careful because we don't want to confuse that with P for pressure. So this is the Greek letter rho for density. SI units for density are kilograms per cubic meter. Now, both in the textbook as well as in the early pages of the test notes, there is a table that has densities in it. It has a lot of other things as well, but density is one of the columns listing values for a number of common materials. So density is something that is unique to the material itself. So water has a specific density, lead has a specific density, aluminum has a specific density. And that density is always able, we can use that to relate that to mass and volume. But when we talk about fluids, we're typically talking in terms of densities as opposed to masses. All right, so coming back to pressure, a Pascal, when we talk about atmospheric pressure, one ATM, atmospheric pressure at sea level, 1 ATM, the conversion is 101,300 pascals. This conversion is known more specifically, more accurately. Our author chooses to round it to this value of 101,300 pascals. You will also see that written as 101.3 kilopascals. So we will be converting back and forth between ATM and pascals as we solve different problems. Now at the altitude in Salt Lake City, our atmospheric pressure is not 1 ATM. We're a little bit lower. And that's because we are farther from the Earth. If we think about the Earth's atmosphere, so we have the Earth, we know gravity pulls in all the little air molecules all around the Earth. I'm not going to draw them all the way around because that's a lot of dots. Gravity is stronger, the force of gravity is stronger closer to the Earth, which makes the density and pressure larger, closer to the Earth. As we go outwards away from the Earth, closer to outer space, the density and pressure are smaller. And so at the elevation of Salt Lake City, our air pressure, our atmospheric pressure, is not exactly 1 ATM. It's a bit smaller, which is actually partly why a lot of athletes come to Salt Lake to train. The atmospheric pressure being lower puts a different strain on the body to breathe and to exercise, and it helps in their training to prepare for different locations in which they might compete. We will, though, for just simplicity's sake, any problem that we're solving that needs pressure, atmospheric pressure, we will go ahead and assume 1 ATM unless the problem itself tells us otherwise, just to keep things on the simpler side. So some of our main concepts, just as we start into fluids, is the concept of pressure being force per area and density being mass per volume. Density and pressure are related when we're talking about like our atmosphere, as I just mentioned. The density, because gases are compressible, the density is larger closer to the Earth because of how gravity is acting on the different air molecules. Now, in terms of pressure in general, let me scroll this up. You might have know something a little bit about hydraulics. You might not, it's okay. This is a very simplified explanation. It turns out in any given fluid, so say I have a syringe or a bicycle pump that's closed off. If I push on this piston, so I'm increasing the pressure in here, any increase or decrease in pressure on a system of fluid that pressure must be transmitted throughout the fluid overall. And so if we're talking like a syringe, a needle where someone is injecting medicine of some sort, this pressure applied at the end causes all of the fluid to have the same pressure, which in turn, of course, it pushes the fluid out the end. The idea behind hydraulics is if I have a region that has a small area connected to a region that has a large area. I can actually lift something very massive. For example, a car. This is, of course, not how the hydraulic system looks like, but fundamentally, I have a big car that I need to lift in the auto shop in order to fix it. If I push with some sort of force on this left side, a different force is experienced on the right side. I'm going to call that F sub R for F right and F sub L for force left. In here is going to be some sort of hydraulic fluid that is incompressible. As the pressure changes on the left side because of that force on the left side, that pressure is equally transmitted throughout all of the fluid. And so we can say the pressure on the left, because of that push downwards, has to equal the pressure on the right side. Now, pressure being force per area, force on the left side, area on the left side, is going to equal force on the right side over area of the right side. The force on the right side, that upward force on essentially the car in this case, ends up equaling this ratio of the areas. So the area on the right side over the area on the left side times the force on the left side. So for example, let's say, just to make up something simple, the area on the left side was 1 meter squared. Area on the right side, 4 meters squared. Just the area 4 times bigger. Really, 4 would be really large, but that's okay. If I applied a force of, say, 100 newtons on the left side, the force on the right side, because the area on the right side is 4 times larger than the left, the force on the right side is 4 times larger. Force on the right side. I don't know what I just said. The right side's force is 4 times bigger because that cross-sectional area that is essentially going to lift the car is 4 times bigger. And so we essentially get a larger force out because of that pressure being transmitted through equally. So the same pressure on both sides, but more force because of that larger area. Now, it might seem contradictory to have more force out, because that kind of seems like getting something for nothing, but that ends up not being the case. The volume of the fluid moved has to be the same. So on the left side, if we think about a column, the volume of that fluid that moved on the left side has to equal the volume of the fluid that moves on the right side. So the cross-sectional area times the distance, however far that portion ends up moving, has to equal that cross-sectional area on the right side times the distance moved. But a column that is long but small area would equate to a larger area and a smaller length. So essentially, the piston on the left side would move much farther down compared to the distance the piston on the right would move upwards. And so this idea of hydraulics, we just use this concept of pressure and pressure transmitting through a fluid within a system. We can use that to get larger forces out, and we can use that to lift heavier objects, which is actually pretty cool. We're going to talk about pressures in fluids, pressure versus depth. So how a pressure gets larger as we go deeper and deeper into a fluid. One other concept that I'm just remembering I need to mention, and that is the concept of gauge pressure. Gauge pressure. If you've ever checked the air pressure in your tires, whether it's on a bike, a motorcycle, a car, the gauge you're using when you are reading it, you're actually reading the difference between the pressure of the gas in the tire versus atmospheric pressure. P naught is going to be the symbol we use to represent atmospheric pressure. So the gauge itself is not telling you directly the pressure inside, it's telling you the difference. And you need a difference so that the pressure inside is pushing outwards on the tire to keep them inflated. Fire marshals have to come and check fire extinguishers regularly. And the fire extinguishers will also have a gauge pressure, which in turn means the pressure inside the fire extinguisher is greater than the atmospheric pressure. And that's important because if we go to use a fire extinguisher, we pull the pin, pull the nozzle or compress the nozzle, the pressure inside needs to be bigger than the pressure outside. So when the nozzle is triggered, I don't know the right word for that particular application, but when we go to use the fire extinguisher, the higher pressure inside pushes the fluid out into the atmosphere. If there was no difference in pressure, then nothing would happen when we pull the trigger on the fire extinguisher. So that difference in pressure is needed in order to be able to use the fire extinguisher for useful purposes. Similarly, for our tires, be it a bicycle or a car, whatever, the pressure inside needs to be larger than the atmospheric pressure in order to keep the tires inflated. And of course, if we get a hole in the tire, the air comes out and we get a flat tire. Ultimately, though, gauge pressure is simply the difference in pressure between inside the system and the atmosphere outside.